What if I told you that the entire universe, with all galaxies, stars, and planets, began as a single point? What if I propose that everything we see around us, from the vast expanse of space to the fleeting dance of particles, emerged from this cosmic singularity in an event known as the Big Bang? The story of the Big Bang theory is a journey of cosmic exploration, one that begins with a fundamental question. How did it all begin? It's a question that captivated the minds of astronomers, physicists, and philosophers for centuries, driving humanity's quest to unravel the mysteries of the cosmos. As we peer through the scientific information, we discover a universe in motion. A universe where galaxies are not anchored in place, but are hurtling away from each other, carried along by the expanding fabric of space itself. This revelation raises a profound conundrum. If the universe is expanding today, what does that imply about its origins? Guided by the visionary insights of Albert Einstein's theory of general relativity, scientists have embarked on a quest to trace the history of universe back to its beginnings. Their journey has led them to the threshold of creation itself, to a moment frozen in time when the cosmos burst from a primal fireball, forever altering the fabric of reality. But the Big Bang is more than just a scientific theory. It's a cosmic epic, a saga of cosmic birth and evolution that invites us to contemplate our place in the vastness of space and time. It challenges us to peer beyond the veil of observable universe and glimpse the mysteries that lie beyond, beckoning us to explore the deepest recesses of existence. So, let us embark on this journey together, guided by curiosity and fueled by wonder, as we delve into the heart of the Big Bang and uncover the secrets of universe origin. As we stand on the cliff of cosmic exploration, poised to delve into the depths of universe infancy, let us now journey back to the primordial moment when time itself began and witness the awe-inspiring birth of the cosmos. About 13.7 billion years ago, the entire universe was incredibly small and hot, all squished into a tiny point called a singularity. Then something remarkable happened. The universe suddenly started expanding incredibly fast, much faster than anything we can imagine. This rapid expansion is called cosmic inflation, and it only lasted for fractions of a second, that is 10 to the power of minus 32 of a second. After this rapid expansion slowed down, the universe started cooling and filled up with different kinds of particles and energy. This process is called reheating. As the universe cooled, these particles started coming together to form atoms, stars, galaxies, and everything else we see in the cosmos today. So, in simple terms, the Big Bang wasn't just a big explosion. It was the start of everything, with the universe rapidly expanding from a tiny hot point to what it is now. Just after the Big Bang, the universe was intensely hot, about 10 billion degrees Fahrenheit. It was filled with the fundamental particles like neutrons, electrons, and protons, which are the basic building blocks of everything we see today. This early universe was like a dense soup of particles, so thick that light couldn't travel through it easily. Light would scatter off the free electrons in the soup, similar to the sunlight scattering of water droplets in clouds. As a result, the early universe was opaque and you couldn't see through it. Over time, as the universe expanded and cooled down, electrons combined with nuclei to form neutral atoms. This allowed light to finally shine through. About 38,000 years after the Big Bang, the light that finally traveled through space is called cosmic microwave background. It's like an afterglow of the Big Bang, a faint glow of light left over from the early universe. Scientists predicted its existence in 1948, and it was accidentally discovered almost 20 years later. Aaron Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey in 1965. They were trying to build a radio receiver but found it was picking up higher temperatures than they expected. They thought it might be because of pigeons nesting in their antenna, but even after cleaning up and getting rid of pigeons, the strange temperatures persisted. At the same time, another group of scientists from Princeton University, led by Robert Dick, was looking for the evidence of something called the cosmic microwave background, a faint glow left over from the Big Bang. They realized that Penzias and Wilson's strange observation matched what they were looking for. Both groups published their findings in a scientific journal in 1965, showing that Penzias and Wilson's accidental discovery was actually evidence of CMB, confirming an important prediction about the early universe. But how people discovered CMB is a fascinating story that connects directly to our understanding of the Big Bang. By stumbling upon this faint glow from the early universe, scientists gained crucial evidence to refine their models of how the universe began and evolved. Scientists are trying to understand the Big Bang, even though we cannot see it directly. One way they are doing this is by using computers to simulate different versions of the universe. Think of it like trying to guess what a baby photo of universe might look like, based on what it looks like now. In a 2021 study, researchers simulated 4,000 versions of the universe on a supercomputer. They compared these simulations to what we know about how gravity works in the early universe. By doing this, they hoped to figure out what the universe might have looked like right after the Big Bang. Another way scientists are studying the Big Bang is by looking at the difference between matter and antimatter. Matter and antimatter are two types of particles that have opposite properties. Matter is what makes up everything we see around us, including ourselves. It's composed of particles like protons, neutrons, and electrons. These particles have positive, negative, or neutral electric charges. Antimatter, on the other hand, is made up of particles that have properties opposite to those of matter. For example, an antimatter of a proton is called an antiproton, and it has negative charge instead of positive one. Similarly, an antiparticle of an electron is called a positron, and it has a positive charge instead of negative one. In a 2020 study, researchers suggested that dark matter, a mysterious substance that doesn't interact with light, might be related to this difference. They think that right after the Big Bang, the universe might have made more matter than antimatter, leading to the formation of dark matter. As scientists explore different methods to understand the Big Bang, from computer simulations to investigations into fundamental particle interactions, they also seek to uncover clues about the age of the universe and its fascinating origins. A lot of scientists have studied the cosmic microwave background, which is like a faint glow left over from the Big Bang. One famous mission that did this was NASA's Cosmic Background Explorer satellite in the 1990s. After COBE, other missions continued studying the CMB, like the Boomerang experiment, NASA's Wilkinson Microwave Anisotropy probe, and the European Space Agency's Planck satellite. Planck, in particular, gave us really detailed maps of the CMB. When its observations were released in 2013, they showed that the universe is a bit older than we thought, 13.82 billion years instead of 13.7 billion years. Planck is still working, and scientists keep releasing new maps of the CMB to learn more about the universe. The maps of the cosmic microwave background show some surprising things. For example, the southern hemisphere of the sky appears slightly warmer than the northern hemisphere. This is unexpected because the Big Bang theory predicts that the CMB should be mostly the same everywhere. Studying the CMB also helps astronomers understand what the universe is made of. They have found that the most of the universe is made up of things we can't see or detect with our usual instruments. We call this mysterious substance dark matter and dark energy. In fact, about 5% of the universe is made up of the stuff we are familiar with, like planets, stars, and galaxies. The rest is this mysterious dark matter and dark energy, which we are trying to understand. As scientists delve deeper into the understanding of the age of the universe, they also explore phenomena like gravitational waves, providing insights into the universe history and evolution. Astronomers are studying how the universe began using creative methods and mathematical simulations. They are also looking for evidence of rapid inflation right after the Big Bang. They are doing this by observing gravitational waves, which are tiny ripples in space caused by big events like black hole collisions or the birth of the universe. According to theories, the universe expanded incredibly fast in its first second, faster than the speed of light. This expansion created the cosmic microwave background and a similar background noise made of gravitational waves. In 2014, astronomers thought they found evidence of these waves using a telescope in Antarctica, but later realized it was likely just dust from our own galaxy. However, since then, gravitational waves has been confirmed to exist and have been observed multiple times, particularly from collisions of black holes. While gravitational waves offer insights into cosmic phenomena like black hole collisions, they also promote questions about the nature of events surrounding the Big Bang, challenging popular misconceptions such as whether the Big Bang was simply an explosion. The term explosion can be misleading when describing Big Bang. In a typical explosion, fragments are thrown out from a central point into space that already exists. However, the Big Bang was different. It was an explosion of space itself. This means that all the distance between objects in the universe are stretching out equally. Imagine a balloon being blown up. As it expands, all the points on its surface move away from each other, just like galaxies in the universe. So, the Big Bang wasn't an explosion in the traditional sense. It was the stretching and expanding of space itself. While the term explosion may be misleading when describing the Big Bang, it helps us understand the concept of the universe expansion, which involves the stretching and spreading out of space itself, and opposed to fragments being flung out from a central point. The universe is expanding at an accelerating rate, causing distant galaxies to move away from us faster and faster. Eventually, this expansion will be so rapid that even light wouldn't be able to reach us from those galaxies, making communication impossible. Some scientists propose the multiverse theory, suggesting that our own universe is just one of many. According to this idea, different regions of space-time underwent rapid expansion, creating separate universes with their own laws of physics. Additionally, some scientists suggest that the Big Bang might not be a one-time event. Instead, the purpose that our universe undergoes cycles of expansion and contradiction, with periods of rapid inflation followed by deflation. This cyclic model offers an alternative expansion for the universe's origin and evolution. The Big Bang theory stands as our best explanation for the origin and evolution of the universe. By studying the CMB radiation, gravitational waves, and the accelerating expansion of the cosmos, scientists have pieced together a compelling narrative of our cosmic history. By the way guys, I also made the videos regarding the parallel universe and the quantum realm and wormholes. If you want to know about them, please go and check the links in the description. And that's all for now guys. If you like this video, give it a big thumbs up and subscribe to my channel. Thanks for watching.